there's an explosion of energy over our heads. As our planet churns nitrogen, oxygen, water vapor, and other gases into a potent brood known as weather. Clouds, storms, the rush of wind, it's all energy in motion. Meet our Jason Host researcher and NASA scientist Robbie Hood. She takes to the skies to study Earth's most volatile weather systems, like hurricanes and tropical storms, up close and personal.
Weather, that's really the relationship of how the atmosphere works across the whole globe. Extreme weather events have such a significant impact on our society. I think it's very important for us to understand them to the best that we can.
You're going to join Robbie in the epicenter of some violent storms. Your mission? Pursue energy through the intricate pathways of the water cycle as it fuels monster storms.
And we're able to process the data.
But first, you'll need some basic tools and skills. You'll need to understand the structure of air, describe the water cycle, explain how clouds indicate weather. Let's take a look at the structure of air. Air is a mixture of atoms and molecules in a gaseous form. But these atoms and molecules are not packed together like in liquids or solids. They're moving constantly, which ensures that they remain evenly mixed in the air. On a large scale, that mixing is called wind.
To study the weather, you need to understand all the relationships. And wind is one of the primary forces that moves weather from place to place.
All gases and mixtures of gases, like air, have two important properties we have to remember. They lack a definite shape, and they lack a definite volume. These properties, combined with the uneven heating of Earth, create higher and lower density parcels of air, more often called high and low pressure areas in the atmosphere. Also important to know are the layers of the atmosphere. Robbie's work is concentrated in the lower two regions, the troposphere and the stratosphere. The troposphere is the region where most of our weather takes place, comprising the closest 14,500 meters to the Earth. The stratosphere continues higher to about 50,000 meters. Now that we know the structure of air and atmosphere, let's examine the water cycle. What is water? You can touch it, taste it, even hold it. But water is not always a liquid. It can freeze solid when it's cold, or evaporate into a gas when it's hot. In all its forms, water circulates throughout our planet. This water cycle has been swirling for billions of years. Energy from the sun heats water until it evaporates and rises into the atmosphere. As the air cools, the water vapor condenses. We see this as clouds. Eventually, the condensed water becomes too heavy to remain airborne and falls back to Earth. And the cycle begins again.
Precipitation, that's my favorite. That's the thing I like to study. So even though I'm studying hurricanes, I'm interested in the whole thing and how everything works. But the fascinating part is the rainfall and the relationship of thunderstorms embedded into the hurricane and how that might be a signal for what's happening to the intensity. Well, this is a sample of some instrumentation from a hurricane. This is one instrument. It's actually looking down on top of the hurricane. It's like looking on the top of a birthday cake so that you can see all the icing. And it actually has 4 different frequencies that can sense different parts of precipitation structures inside the hurricane. For example, this particular picture is looking at the heavy rains down close to the ocean surface, while this is looking at the ice structures that are higher up in the hurricane structure. Now, to also look at the same thing from a side angle, just like slicing a birthday cake and looking at the individual layers, this was collected by a different instrument, and this is looking slicing through the storm, the vertical profile of the precipitation structure, and it's showing liquid rain here and then ice crystals above. And by using these two together, we can map out what the precipitation features are of a hurricane, and understanding how those precipitation features change help us understand how energy is translated throughout the hurricane and how the whole hurricane is working together.
Now let's look even more closely at the relationship between energy and water in the atmosphere. Measuring how much water is in our atmosphere is the key to understanding weather systems. As molecules of water rise into the atmosphere, they condense onto particles of smoke or dust, changing from gas to liquid. Get enough together, and clouds form. As water vapor condenses to form clouds, energy is transferred to the surrounding air. When the conditions are right, this release of energy can transform beautiful cloud formations into monster storms. From wisps of cirrus clouds that denote fair weather to gray and heavy cumulonimbus clouds about to burst.
Basically, a thunderstorm or a hurricane, they start from basic cloud structures and they build into entities that start to work together and have more, we call them a convective nature.
The formation of clouds, then, is heavily dependent on dew point. Dew point is the temperature at which water vapor begins to condense into liquid water. When it cools past this critical point, the water vapor condenses into droplets. Then the droplets collide and combine until they become big enough to fall back to Earth, pulled by gravity. It's a critical measurement in understanding weather. Robbie flies directly into monster storms to gather critical information about energy and weather. She and her team drop electronic instruments called dropsondes that record data as they drop to the ground.
I personally do a lot of aircraft research, and the reason we do an aircraft, NASA does an aircraft field campaign, is we have satellites that are looking at the big picture, and the satellite can't always see the detail, particularly of a hurricane, can't see all the detail.
The data collected by Robbie and her team may provide clues to how hurricanes gain energy, speed, and potency as they move from ocean to land.
The main goal that we have for Earth science within NASA is to improve our understanding of the whole global system using satellites. We want to improve our understanding and provide greater societal benefit with our observations. And our vision of the future is to have a complete Earth observing system that encompasses observations from many different levels, including satellites, suborbital platforms like aircraft and unmanned aerial vehicles, ground-based instrumentation and ships, ocean buoys, all kinds of things, and to have that whole network actually working together to gain the best three-dimensional picture of what's happening in the environment. So we're really looking to the future to have everything as automated, and so that we can use data faster and to be able to do predictions of the upcoming phenomena faster. And if you can do that, then you've got a better forecast, so people can be better informed even in real time.
A better understanding of these storms could potentially save lives. So let's recap. We can now understand the structure of air, describe the water cycle, explain how clouds indicate weather. Your briefing is complete. Now it's time to move to the next part of your mission.
Now with your table group, discuss the following ideas. You may need to switch back from slide to slide, but when you are finished discussing each of the questions or ideas, please take out your clouds in a bottle lab sheet and continue on with the module. First question, do you understand the structure of air? Second question, can you describe the water cycle? Third idea, explain how clouds indicate weather. And fourth question, how are clouds formed?